Okay, so if you haven't already drawn a copy of the unit circle, and if you're not already aware, I'm now recording this, so you make a choice about whether you want your voice to be that annoying voice in the background underneath. I'm going to talk about the unit circle, but before I do any talking about the math behind a unit circle, I need to decorate my unit circle a little bit. So I'm going to choose an annoying colour. Maybe we'll do red because the circle's red. I'm going to go around and plot some coordinates and talk about some important aspects of the unit circle. So firstly, the unit circle is our way of representing an angle from the positive x-axis. Now, the unit circle has a radius of 1, which I'll show you in a minute, but we start at the positive x-axis, and so that means that this unit circle starts here at 1, 0. That's the coordinate there. In fact, I'm going to make my unit circle a little bit smaller, and then I'm going to zoom in on a bit so my writing's a bit bigger. There we go. 1, 0 is there. And going around, I've got my other coordinates. This coordinate at the top here is 0, 1. Reggie, what's this coordinate?
Sorry, that one would be -1, 0.
Thank you. Harvey? 0, -1. Excellent. So there's my 4 coordinates around the unit circle. It has a radius of 1, so it goes around on through the axis intercepts of 1 and -1. And if I plot a point, this will be our common point here, which I'm going to plot just randomly in what we call the first quadrant. And I'm going to call that point P, X, Y. It also has a radius of 1. Now, I've chosen this point in the first quadrant, but it could be anywhere. We'll talk about that a bit later. This point will make an angle of theta with the positive x-axis. So you'll have to start getting used to the fact that everything is now measured from the positive x-axis for this whole topic. And realistically, the only time we don't measure from the positive x-axis in an anti-clockwise direction is if you're dealing with bearings. Otherwise, it's going to be this way all the time. So I've denoted the point on the outside here, and from the positive x-axis around to that point is my angle theta. If I start on the positive x-axis, how big is the angle theta? Sophie, if I start on the positive x-axis, how big is the angle theta? 0, thank you. Good answer. You're recorded saying 0 now. Thanks.
I'm so smart. I'm recording.
0 degrees. And as I go around, if I go around so that I'm at the point 0, 1, what angle is that? 90, thank you. And continue around, what do I get when I go across to the... And 270 down here. And then we're back to 0. But 0 might also be 360 degrees. And we can carry on around the circle adding to that. We'll talk about that in a minute. What is it in radians? What's 0 degrees in radians?
0.
Thank you. So that's 0 radians. And what's 90 degrees in radians? Half pi. Let's go pi on 2. And what's 180 degrees in radians? This one's easy, Mitch. Pi, thank you. Sophie. And what is 270 degrees in radians? No, you've already answered one. Eddie, no?
Is it 2 pi?
Not 2 pi, that's 360. Too far. You've already answered one. Anybody else who hasn't answered one?
3 pi.
3 pi on 2. Thank you, Jackson. 3 pi on 2. That is what you said, isn't it?
Yeah.
Okay, good. 3 pi on 2, and we get back to 0, and we also have 2 pi there. So there's our measure. Remember, this angle theta is a measurement from the positive x-axis around our unit circle. Now, here's where the magic starts. Let's imagine that I get that radius I've drawn there with theta, and I create a triangle out of it. So I'm just going to drop a little vertical line down here. And the position on the outside of the circle is P, X, Y. So I've given it the coordinate, X, Y, which means my horizontal distance is X. And my vertical distance is Y. Look at that arrow. How nice and straight is that? It's a ghost arrow. Any questions on that? Happy with that X and Y placement? So that's how coordinates work. You know the coordinate system. You learn it in year 6, 7, whenever it was. And you know that's how it works. What I'm going to do now, though, is we're going to talk about some trig within this triangle. So I want to ask you, given that we know the hypotenuse is 1 the opposite side is y, and the adjacent is x, somebody who hasn't answered a question yet, I would like to know what sine of theta is equal to. Pascal. It will be y. Can I just take it a step back? Sine of theta is y over 1, which is opposite over hypotenuse, and we can simplify that down to be y. So can you see that sine of theta equals y, or y equals sine of theta? I can actually write this on here. The height of my triangle is sine of theta. Now, I know it looks like I've just picked one point here, but I've generalised this. I've said P is on the outside of the circle somewhere, such that I get the coordinate x, y. This is actually making the statement that sine theta is always the height of this triangle. In fact, depending on the angle, sine theta is always the height of the triangle formed by that angle. And that's going to be really important as we move forward with this topic. So now let's see if there's another relationship here. Light blue. I'll test it out. Cos theta. Somebody else new? Do you want to step in here? You know this one, do you?
It'll be x over 1.
X over 1, which simplifies down to x. And so I could write down that cos theta is down here, couldn't I? Yeah? And so now I've got cos theta and sine theta equal to my x displacement and my y displacement in that order. And I can use that to represent my position on that unit circle as I travel around based on an angle theta. Any questions on that? It probably seems a little bit like, well, okay, I can see you're excited. I'm not so much. But why? What does this matter? And I can see that, and we'll get a bit more into it. It's got some really important properties. In particular, the end game really for us in this topic will be solving trig equations using this, because your calculator is a little bit restricted. When you solve a trig equation in your calculator, it will give you one answer. But actually, when you do solve a trig equation in real life, there are an infinite number of answers. And it's this unit circle that will allow you to get all of the answers. So we'll be using it a lot. But we've got a couple of weeks to get to that point. Because we're on a bit of a roll, I'm going to do one more. And I've got one colour left, so I'll use that. What about tan of theta? Somebody different. Somebody back table, different person who hasn't answered the question. Mason. Y over x. Excellent. So tan is, Connor? Tan is cos theta. Sine theta over cos theta. Tan is opposite over adjacent, which gives you y over x, which gives you sine theta over cos theta. And that will be an important little relationship for later on. This is actually called an identity. The reason why it's called an identity rather than an equation is if you pick an angle, any angle, doesn't have to be between 0 and 360, it can be any number for an angle, and you put it in here, do sine of that angle divided by cos of that angle, it will be equal to tan of that angle. And you're welcome to test that out now if you want to. But I now know the people that just picked up calculators don't trust me. So that's great. So that relationship's true. We'll come back to that. That's there. But it's not as nice as the sine and cos. It doesn't represent very well on here. It doesn't give us anything tangible on our diagram at the moment. And actually, as you move forward and we do more applications, you'll see sine and cos comes up a lot more than tan. So that's kind of where we're at there. So I'm going to ask you a couple of questions now regarding calculating particular angles. So I'll come back up to this. I just want to see the questions. Sine and cos. There we go. The first two questions are, I'd like to know the value of sine pi on 2 and cos of pi. So I'd like you to have a look at this, talk on your tables. I'm going to give you about a minute to see if you can work out the value of sine pi on 2 cos of pi, and do it without touching your calculators. That's your challenge. Diagram's there, all the information you need is actually there. And then I'll take you through it. Which one? The second one? Yes, I'll show you why. Okay, ladies and gents, here are my 5 examples. And I've just copied this, transposed this unit circle down. So that's our unit circle we've been working on. Is that all right, Sophie? Excellent, good. That's our unit circle we've been working on. And there are examples which I've just asked you to have a look at. So I'm going to probably completely ruin this unit circle, so there's a better copy up above now. Let's start with sine of pi on 2. Can anybody tell me anywhere, describe to me, where on this circle is the angle pi on 2 representing?
90 degrees.
90 degrees, which is where on the circle?
The very top.
The very top. I'll take that description. So 90 degrees is right at the top. Everybody agree with that? And sine theta represents what part of that triangle?
The vertical.
The vertical distance. See how sine theta is on that vertical part of the triangle? Cos theta is on the horizontal. So if the triangle was here, and it's not really a triangle at 90 degrees, it's more like a straight line, how tall is it?
1.
It's 1. Did anybody put it in their calculator, by the way? If you're looking at your calculator now, if it's in radians, we did talk about swapping it over and stuff, so you might be anywhere at the moment. If it's in radians, do sine of pi on 2. If it's in degrees, do sine of 90. And you should get 1, because it's the height of that triangle, it's the height of the point PXY. And when you're at 90 degrees, the height is 1. So we get sine of pi on 2 is equal to 1. And that comes straight from our unit circle. What about cos of pi? Where's pi? Can somebody describe to me where pi is on this circle? Yeah. The left side, the furthest left point on this circle. There's pi over here. You'll notice all these questions are only to do with these critical points around the side that meet the axes at the moment. We'll extend that in a minute. Over here, remember cos is the x displacement of the triangle or the point PXY. So if we're around here, how far away along the x-axis from the centre?
-1.
-1. Did anybody do cos of pi and get -1? No? Did anybody do cos of pi and get something different? Good. That's the important thing, I suppose. Okay, sine of 7 pi. Here's my next question for you. Anybody want to talk to me about sine of 7 pi?
Sine of 7.
It goes 180 degrees 7 times.
180 degrees 7 times. Can you visualise, if I go around half a circle 7 times, where do I end up? Starting here?
It's 1, 2, 3, and then back to 180.
Okay, good. 1, 2, 3, and back to 180. So 7 pi is 3.5 times around the circle. It's equivalent to what?
-1.
Say it again, sir?
-1.
It is equivalent to -1. Cos of 7 pi is equivalent to -1. This question is sine of 7 pi, but that's not the question I asked. 7 pi is 3.5 rotations around. So that's the same as doing what? You end up in the same place as just pi. Just pi, that's right. Or you end up in the same place as 3 pi. 3 pi is 1.5 times around, isn't it? Or 5 pi. Or 111 pi. Or negative pi. There's lots. So sine of 7 pi, and this is going to start you on your road to symmetry, by the way. I'm going to make the statement this is the same as sine of pi. Is everybody happy with that? 7 times around, 3.5 times around is the same as half a time around, which is just pi. And what's sine of pi? It's not 1?
Not 1.
It's 0. Look, sine is the height. What's the vertical displacement when we're around here?
-1.
We're at the same height as the origin, aren't we? So we have our coordinate here. The y value in our coordinate is 0. We're not up or down. So we get 0. Cos of negative pi on 2. I've kind of alluded to this one a little bit a moment ago because I made a mention of a negative. So where do you think we go if we're moving in a negative direction?
Oh, yeah.
So we normally go this way, but if we're moving in a negative direction, we go down pi on 2. So what do you think the value of cos of negative pi on 2 is?
0.
Who's saying it?
0.
You're saying 0. Can you explain to the class why?
Honesty.
I thought you negative 1.
Okay, what do you think it is?
Is it because there's no horizontal change from the center point?
It's the same.
There's no horizontal change from the center point.
Excellent. So cos of negative pi on 2, negative pi on 2 is backwards. In year 11, you can still think about this like degrees. So pi on 2 is 90 degrees, backwards 90 degrees. And cos is a horizontal displacement from the origin. Here, we haven't moved either way from the origin. The x-coordinate is 0. So we've got cos of negative pi on 2 is equal to 0. It's also equivalent to a quarter rotation back is the same as a 3/4 rotation forward. So it's the same as cos 3 pi on 2. Last one. And it's going to rely on a rule, which you might want to write down. I'm just going to write them down up here very quickly. Here's 3 rules, and they're true, and they can be extended. This is not a generalization yet, so it's just a start to the rules. What sign, when you get an angle and you add 2 pi to that angle, what sign of the new angle equivalent to? We don't know theta at this point, so it's a generalization. Anybody got any thoughts on what this generalization might be leading to? Or what point I'm trying to make loosely?
And no matter, as long as you're on the same point in the end, it doesn't change. So 2 pi is just a 360 rotation.
Yep.
So you always end up on the same point or degree.
So you'll be in the same point as just theta?
Yes.
So can everybody see that this will be the same as just sine of theta, whatever theta is? So I'm making the connection here. I'll bring this connection back in a minute, but you might want to write this down. Cos of theta and tan of theta. And the big point I'm making is if you rotate around 2 pi, which is 360 degrees, in either direction, you end up back where you started. And you all just anecdotally did that before anyway, with the cos of 7, sine of 7 pi. And you know, that was 3.5 rotations, which is the same as half a rotation. So the same thing here. That 2 pi is a special number. That's a full rotation. So if we add 2 pi on, we end up in the same position. Add 2 pi on again, same position. If I want to fully generalize this, I might say theta plus or minus 2 pi k. So any number of 2 pi's. Any number of rotations on a circle, I end up in the same position. And so that's an important thing to recognize. You probably won't really use that rule. As long as you recognize that rule and you understand you can just take out multiples of 2 pi and you end up in the same place, then you can simplify any problem. And for question E, that's going to be really important. So I'm actually going to go down and do question E and then come back to this statement for those people that are going to throw a calculator at me if I move down. Here's question E, and I will come back to that statement. Sine of 127 pi over 2. So my very direct question to you is, how many 2 pi's are there in 127 and what's the remainder?
3 pi over 2 is the remainder. Oh, well, that's what it will equal.
61.
60 with a remainder of 1 pi over 2.
60.
It's 63 remainder 1.
63 remainder. Can I just go on this thinking, by the way? It is 63, you're right. And it's got a remainder of pi and 2. But I quite like this because 127 is a big number. And unless I set up a really specific procedure with you, it might be hard to get our head around it. But what if we looked at this and said, you know what? I can see there's 60 pi in here, which is 60 is 120 over 2. And if I take out the 60 pi, I'm left with just 7 pi over 2. And that actually simplifies the situation a bit. Maybe it helps us a bit. So I might just change this to be, and this is an in-between step that you don't really need, but I'm hoping it might help some of your thinking. If I change this to 120 over 2, 120 pi, sorry, over 2, plus 7 pi over 2, can you see that that is sine of 60 pi plus 7 pi over 2? So I've just taken out 120 pi. It's not the best result, but it might make things a bit simpler if you can't really work it out at the top of your head. And actually, that's going to be my remainder here. But 60 pi just means I've gone around that circle 30 times. Yeah? And I'm back where I started. So I don't even need that 60 pi. I'm going to get rid of it. I'm doing this question because there's a couple of questions in the exercise similar to this magnitude. That's a bit easier to work with. How many rotations around a circle is that?
3.5.
I think it looks to me a bit like it is 1 3/4 rotations around a circle. What's one full rotation around a circle? 2 pi. So I'm going to take out another 2 pi because I can. What's 2 pi as a value over 2?
Just one.
You've gone the wrong way. 4 pi over 2 is 2 pi. Does everybody see that? I've just broken that 7 up again. This is just fraction work, like year 7, 8 fraction work, but I'm working in the opposite to what you've done in the past. So I've broken it up into 2 parts. All I'm doing is recognising that 2 pi is the same as 4 pi over 2 and taking that out. So I can get rid of that, and I'm just left with sine of 3 pi over 2. And then I go to my unit circle over here. I can see where 3 pi over 2 is. It's down the bottom here. And sine, remember sine is the vertical component. What's sine of 3 pi over 2? -1. Done. I know, you know what else you could do though? Some of you are looking at me like, oh, I hate that. So what if I just tell you this? Sine of 127 pi over 2 is equal to, let's just for a moment forget the pi. Can somebody on their calculator tell me what 127 divided by 2 is? 63. Sine of 60, oh that's wrong, 63.5 pi. 127 over 2 is 63.5, yeah? What's the highest even number I can take out of 63.5? 64 is a bit too big, so 62 I'll take out. That leaves me sine of 1.5 pi, and sine of 1.5 pi is exactly the same as sine of 3 pi and 2. So if you can't deal with the fractions, that's not the end of the world. Just deal with the decimals. I would prefer to deal with the fractions. It makes it a bit easier for me, but it might not make it easier for you. That's about as hard as these questions today get. And you can now do, obviously you need to do 15A for me. 15D we talked about last lesson, but it's just a revision of year 9 trig. 15B we've just done. And we've got a little bit more work before you can do 15C, but most of you probably had to do it anyway because it's just tan, but equivalent. So 15B for me, yeah.